From food to pharmaceuticals, proteins, fats, minerals, leather and fertilizer, one animal can generate an extraordinary network of industrial products. From food to pharmaceuticals, proteins, fats, minerals, leather and fertilizer, one animal can generate an extraordinary network of industrial products.
This video is not the same. This is a 10 scientific products from pig documentary, and the last one will surprise you. Wait till you see it.
Before processing, the pigs are kept in controlled conditions designed to reduce stress and maintain welfare.
Non-slip floors reduce falls, while drainage systems help keep the environment hygienic.
Ventilation controls heat, humidity, and air quality, while animals wait for processing. Access to clean water helps maintain normal hydration before the animal enters processing. Curved passageways encourage forward movement without forcing animals through sharp turns. This final gate separates the holding environment from the controlled processing area. Stunning is used to render the animal unconscious before slaughter and minimize suffering. The goal is rapid loss of consciousness while keeping the procedure controlled and consistent. After stunning, slaughter is performed rapidly before the carcass enters primary processing. The first major transformation is preparing the skin for hair removal and further processing. The water must stay within a controlled temperature range. Too little heat leaves hair behind. Too much can damage the skin. Hot water scalding softens hair follicles, so the bristles can be removed mechanically. Rotating mechanical scrapers physically remove the loosened hair from the skin.
The removed bristles are collected separately because they can become another industrial raw material.
Controlled singeing removes the tiny hairs that mechanical scrapers leave behind.
Because the skin remains intact, it can later enter a separate leather processing chain.
Pressurized washing removes remaining surface contamination before the next processing stage.
Continuous sanitation helps prevent microorganisms from spreading between processing surfaces.
Rapid processing limits unnecessary delay and helps maintain hygienic control after slaughter.
Incredible, isn't it? And this is only the beginning. Welcome to Factory Scenes, where we take you inside the world's most fascinating factories. Have you ever wondered how the products you use every day are actually made? Here, you'll discover every step, from raw materials to the finished product. Now tell us in the comments what product or factory would you love to see us in could be our next video. Stay with us until the very end. Subscribe to Factory Scenes, and let's get back inside the factory.
Primary cutting creates large sections that can be routed into specialized product lines. Separate materials follow different routes, because meat, fat, skin, and bones require different processing.
These primal sections become the starting material for bacon, ham, sausages, and other pork products.
Controlled chilling is critical, because lower temperatures slow the growth of harmful microorganisms. Refrigerated air removes heat from the meat and slows microbial growth. The engineering challenge is cooling the center quickly while preserving the meat's quality and texture. From one carcass, separate production streams now begin, each engineered for a different final product. The pork belly now enters a specialized line where curing transforms it into bacon. Bacon begins with a controlled curing brine, designed to distribute salt and curing ingredients evenly. Multiple hollow needles inject curing brine deep into the belly instead of leaving the cure only on the surface.
The injection pattern helps distribute the curing solution through the thickness of the meat.
Multiple injection points reduce uneven curing in thick sections of pork belly. Controlled drainage removes excess surface brine before the next curing stage. Gentle tumbling helps distribute the curing solution and improves contact between the meat and vacuum tumbling can improve brine contact while reducing trapped air around the meat. Mechanical tumbling also helps extract surface proteins that improve binding and moisture retention. The cured belly rests under refrigeration, so salt and curing ingredients can diffuse more evenly. Curing takes time because the ingredients must move gradually through the meat. Smoking adds characteristic flavor, while controlled airflow distributes the smoke around the meat. Controlled cooking develops the final texture, while bringing the product to a safe internal temperature. Rapid chilling stabilizes the cooked bacon and prepares it for precise, high-speed slicing. Chilling firms the fat and structure of the bacon, allowing the slicer to make clean, uniform cuts. The roasted and smoked bacon is carefully inspected for consistent shape.
Quality is our top priority.
Each slab is trimmed to perfection. Precise alignment keeps the slab stable, helping the slicer maintain consistent thickness and portion weight. The chilled slab now enters a high-speed slicer engineered for thousands of consistent cuts. A controlled feed rate and blade movement determine how consistently each slice is cut. Uniform slicing controls the thickness, appearance, and cooking behavior of the finished bacon.
Slice thickness changes cooking time, texture, and how quickly the bacon fat renders.
Automated shingling arranges the slices into consistent portions that are easier to package and handle. Automated weighing keeps each package close to its intended target weight. Portion control systems can adjust individual packs when their weight falls outside the production target. The packaging line forms a controlled barrier around each portion before sealing. Vacuum or controlled atmosphere packaging limits exposure to air and helps protect the product during refrigerated storage. A package can look perfect yet have a weak seal. Automated checks help protect product integrity. Finished bacon is labeled, packed, palletized, and transferred into controlled refrigerated storage for distribution. From chilled pork belly to to finished bacon, every stage has a purpose. But another cut takes a very different path, toward ham. Ham begins with a much larger, denser cut, the pork leg, whose structure requires a different processing approach. Deboning removes the central bone and leaves a large muscle structure that can be cured and shaped more efficiently. Trimming standardizes the shape and fat distribution, making later curing, forming, and portioning more consistent. Bacon comes from the fatty belly, while ham is typically produced from the larger muscular leg. Ham curing uses a controlled brine to distribute salt and other curing ingredients through the dense muscle. Because ham is much thicker than bacon, multiple injection points help distribute the curing solution throughout the muscle. After injection, the curing solution gradually redistributes through the muscle during the following processing stages. Gentle tumbling improves contact between the curing solution and the meat, while helping develop the desired texture. Curing and mechanical action help extract muscle proteins that can bind meat pieces together during forming and cooking. A refrigerated resting period gives the cure time to redistribute before the ham is formed. Forming compresses the cured muscles into a uniform shape for consistent cooking and slicing. The mold holds the ham's shape, while controlled cooking develops its final structure and texture. The mold holds the ham's shape, while controlled cooking develops its final structure and texture. Controlled cooking uses temperature monitoring to achieve the required internal heat while protecting texture and quality. After controlled cooking, the once irregular muscle pieces emerge as one uniform ham product.
After cooking, the ham is rapidly chilled to control microbial growth and stabilize its texture.
The center of a large ham cools more slowly, so controlled refrigeration must remove heat safely throughout the product.
Once chilled, the mold is removed, and the ham retains the uniform shape created during cooking.
The formed ham now enters a precision slicer that converts one large block into uniform portions. The uniform cross-section is the result of curing, forming, and controlled cooking before slicing ever begins.
Unlike bacon's layered belly structure, ham is usually sliced from a denser cooked muscle, giving it a different texture and appearance.
Synchronized conveyors arrange individual slices into repeatable portions for accurate weighing and packaging.
Automated weighing keeps portions consistent and helps control the amount of product placed into each package. The packaging machine forms individual cavities around the portions before the protective top film is sealed.
Controlling the atmosphere inside the package helps protect the ham during refrigerated storage and distribution. Controlled heat and pressure create a continuous seal around the package, protecting the product from the outside environment.
Labels provide product information and traceability, allowing finished packs to be tracked through distribution. The finished ham is packed into cases, palletized, and kept under controlled refrigeration until distribution.
A pork leg becomes ham through curing, forming, and controlled cooking. But the next product takes a completely different route. Grinding, mixing, and stuffing turn pork into sausages. Sausage takes pork in a completely different direction, reducing the meat, controlling its fat, and rebuilding it into a new texture. Sausage texture starts with formulation. The balance of lean meat, fat, and other ingredients determines the final bite.
Fat contributes flavor, tenderness, and juiciness, but the ideal ratio depends on the type of sausage being produced.
Industrial grinders reduce chilled pork into controlled particles that can be mixed into the desired sausage texture. Changing the grinder plate changes particle size, allowing manufacturers to control the final sausage texture. The formulation combines meat with salt, seasonings, and other controlled ingredients according to the specific sausage recipe. Mixing distributes the meat, fat, salt, and seasonings so each portion receives a consistent formulation. Salt helps extract functional muscle proteins that improve binding, water retention, and the texture of many sausage products. For finely textured sausages, high-speed cutting disperses fat into a smooth, stable mixture. Not every sausage is made the same way. Particle size creates major differences in texture, appearance, and bite. The casing provides the outer structure that holds the sausage mixture during filling, linking, and cooking. A controlled stuffer fills the casing evenly while minimizing unwanted air pockets in the sausage. The linking machine divides the continuous filled casing into uniform portions at high speed. Controlled cooking develops the sausage's final texture, while smoking can add characteristic flavor and surface color. After cooking, rapid chilling brings the sausages down through a controlled temperature range before packaging and distribution.
Surface preparation helps the casing remain clean and stable before the sausages enter the packaging line.
Optical counting systems can separate individual sausages into consistent package quantities at high production speeds. Portioning organizes individual links into repeatable pack sizes, making the finished product easier to handle and sell.
Sausages can be packaged in several formats, depending on the product, shelf life requirements, and distribution system.
Some sausage packs use a controlled atmosphere to help maintain product quality throughout refrigerated storage.
Seal testing helps identify packaging defects before a finished product enters the supply chain.
Metal detection provides another safety barrier by identifying unwanted metallic contamination before products leave the factory.
Final checks verify package weight, labeling, and traceability before the sausages enter shipping cases.
Individual retail packs are grouped into shipping cases, so large quantities can move efficiently through the cold chain. Robotic palletizing builds stable shipping loads while maintaining a repeatable arrangement of cartons. The cold chain continues through storage and refrigerated transport until the finished product reaches its destination. Pork can become much more than food. Some collagen-rich materials can be transformed through controlled processing into gelatin, a completely different industrial product.
Some collagen-rich pig materials can be transformed into gelatin, turning a processing byproduct into a valuable industrial ingredient.
Gelatin begins with collagen, a structural protein found abundantly in connective tissues and skin.
Careful sorting helps ensure that only suitable collagen-rich material enters the gelatin process.
The material is thoroughly cleaned before extraction, so unwanted surface material does not interfere with downstream processing.
Pre-treatment helps open the collagen structure, so the protein can later be extracted more efficiently. Controlled chemical and thermal treatment changes collagen's structure, allowing gelatin-forming proteins to be extracted into water.
Hot water extraction releases gelatin-forming proteins from the prepared collagen material into the processed liquid. Concentration removes excess water, increasing the gelatin solids before the material is dried.
Gelatin quality can be evaluated by properties such as concentration, viscosity, and gel strength.
Drying removes the remaining moisture and converts the concentrated gelatin into a stable dry ingredient. The dried gelatin is milled into a controlled particle size that can be easily handled and incorporated into other products.
One important property is gel strength. This is the ability of gelatin to form and support a firm gel under controlled conditions. The finished gelatin powder is weighed, sealed, and labeled as a controlled industrial ingredient.
Collagen can become gelatin, but another part of the pig follows a completely different path, through rendering and purification to produce refined pork fat. Separated pork fat can be rendered and purified into lard, giving another part of the pig a useful second life. Before rendering, excess lean tissue and unsuitable material are separated to improve the quality of the recovered fat. Rendering uses controlled heat to release triglyceride-rich fat from the tissue and convert it into a separable liquid. Inside the renderer, controlled heat and agitation release the fat. The remaining tissue becomes easier to separate. Heating disrupts the fat-containing tissue, allowing the liquid triglycerides to separate from the remaining solids. Rendering creates separate streams, recoverable liquid fat, and remaining solid. Centrifugal separation uses differences in density to help remove water and fine solids from the recovered fat. Fine filtration removes remaining suspended particles, producing a cleaner fat suitable for further refining. Deodorization can use controlled heat, steam, and vacuum to reduce unwanted volatile compounds and produce a milder refined fat. Refining changes the fat's physical and sensory characteristics by removing unwanted moisture, solids, and volatile compounds. Controlled cooling determines how fat crystals form, which strongly influences the final texture of lard.
Like other fats, lard changes texture with temperature, becoming softer when warmed and firmer when cooled. Quality testing checks characteristics such as moisture, acidity, and appearance before the refined fat is released.
The refined fat is filled into sealed containers, labeled, and prepared for controlled storage and distribution.
Rendered fat is only one path. Other materials can be processed, producing smaller collagen peptides used as functional ingredients.
Collagen is a large protein. Hydrolysis breaks its long chains into much smaller collagen peptides. Collagen peptide production begins with carefully selected collagen-rich material, whose composition affects the final ingredient.
From the prepared material into a purified liquid phase for further processing.
Large collagen molecules are difficult to handle as intact proteins, so controlled hydrolysis reduces them into smaller peptide chains. Enzymatic hydrolysis uses specific enzymes to cleave collagen's protein chains into smaller peptide fragments. During hydrolysis, enzymes break selected peptide bonds, progressively reducing the size of the collagen-derived protein fragments.
Processing conditions can be controlled to influence the size distribution of the resulting collagen peptides. Membrane separation can help remove larger components and refine the peptide-containing solution. Concentration removes excess water, reducing the volume of liquid before final drying.
Spray drying converts the concentrated peptide solution into a stable, dry powder by rapidly removing moisture from fine droplets. The dried peptide powder is collected in a controlled system to protect its purity and consistency.
Final testing verifies properties such as moisture, protein content, purity, and solubility before release.
The collagen root produces peptides, but the mineral-rich bones follow another path. Crushing, drying, and milling can transform them into bone meal. Bones contain valuable minerals, particularly calcium and phosphorus, making them another useful processing stream. Controlled heat treatment reduces moisture and prepares the bone material for efficient grinding and further processing. Industrial crushers reduce the bones into smaller pieces, increasing surface area processing stages.
After drying, the brittle bone is milled into bone meal containing concentrated mineral material.
Screening controls particle size, ensuring the finished bone meal has a consistent physical form. Bone mineral contains calcium and phosphorus compounds that give bone its structural strength. The finished bone meal is weighed, sealed, and palletized for controlled storage and distribution.
Laboratory analysis verifies mineral composition and helps confirm that each production batch meets its required specification.
The same animal has produced food, fat, protein, and mineral products, but one more material stream can become something completely different: leather. Pig skin contains a dense collagen fiber network that can be stabilized and transformed into durable leather. Tanning chemically stabilizes the collagen fibers, making the skin more resistant to decay and suitable for long-term use. After tanning, controlled dyeing and conditioning give the leather its color, flexibility, and desired physical characteristics. Precision splitting controls thickness, allowing leather to be manufactured for different applications. Finishing improves the surface appearance and gives the leather the physical characteristics required for its intended use.
Finished leather is tested for properties such as thickness, strength, and flexibility before production approval.
Once finished, pig leather can be cut and assembled into products such as gloves, footwear, wallets, and other goods. When collected under controlled food-grade conditions, pig blood can be separated into useful protein-rich fractions instead of becoming waste.
Porcine intestinal mucosal material is an important industrial source for pharmaceutical heparin. Controlled extraction and purification isolate heparin from other biological components before pharmaceutical testing. Because heparin is a medicine, every batch requires rigorous identity, purity, potency, and safety testing. From a porcine-derived raw material, highly purified heparin can become an essential pharmaceutical product.
After food and ingredient production, suitable residual materials can still contain nutrients that can be recovered for agricultural use.
Laboratory analysis verifies nutrient composition, so the fertilizer can be produced to a consistent specification.
Controlled heat, drying, grinding, and blending convert suitable organic residuals into a stable fertilizer ingredient. Recovered nutrients can return to agriculture as fertilizer, completing another cycle from animal processing back to the soil.
After processing, every product enters its own supply chain: food, ingredients, pharmaceuticals, and agricultural materials, all leaving the factory for different destinations.
The next time you see a pork product, remember, its story may begin with one animal, but its industrial journey can lead in many unexpected directions.